Okay, welcome back, everybody. To continue our diversion into a differential geometric description, let's have a look at the kinematics of deformation using this formalism. I think we had this page last time, and we ended last time. So we'll use what we call a convected coordinate system to describe the deformation. We explained it last time. You imagine, for example, here at the bottom of the page, painting a coordinate grid on the balloon and say labeling a one point with its coordinates, say 1, 2 in the coordinate system. That material point carries the same label 1, 2 throughout its motion. So the label associated with a given material point, the coordinate labels never change. This is what I mean by a convected coordinate system. So if isolating attention on a particular material point is the same as focusing attention on a fixed set of coordinates, theta 1, theta 2, theta 3. So these coordinates stretch and rotate with the material as it deforms. And this is nice because we effectively have one coordinate system, even though we have, a continuum of configurations, a family of configurations. So the usual formalism we had before applies. Say small x is parameterized by the convected coordinates, but now, of course, small x evolves with time. But at any fixed time, we can proceed as we did previously in our discussion of geometry to produce, by differentiation with respect to the convected coordinates, produce the natural basis associated with the coordinates in the present configuration, let's say. We're holding time fixed here when we do this, of course. We can form the metric as determinant and so on. And we do the same in our reference configuration, except this position, capital X, now it is a function only of the convected coordinates, not dependent on time. Okay. So again, this defines the position of a particular material point in a reference configuration. That material point is in one-to-one correspondence with a fixed set, theta 1, theta 2, theta 3. So knowing those coordinates is equivalent to knowing the material point you're talking about. We can do the same thing. We can generate a natural basis in this configuration, associated metric. I'll use capital G to go with capital X. Metric, capital Gij, determinant, so on. And all the assumptions we made previously about these curvilinear coordinates apply here also to any fixed configuration. Of course, the configurations evolve with time as well. So we will regard the thetas and time as the independent variables. That's in effect a Lagrangian description of the motion, because taking the thetas and time as independent variables is the same as taking material point and time as the independent variables. So this is inherently a material description, not a spatial description in continuum mechanics. Okay. So that's just to refresh your memory on what we mentioned last time. Okay, well, we can proceed as we did in the earlier discussion, purely geometric discussion in Euclidean space, to write, for example, the differential dx using the chain rule as capital X comma I d theta I, and that brings in our referential basis times d theta I. Likewise, we can do the same with the current position, dx at fixed time, so we're holding time fixed, so dt would be 0. D small x would be, again, x comma I d theta I by the chain rule, and the small x comma I are just the natural basis elements in the current configuration. And because x depends on time as well as the thetas, the g's also depend on time. The capital G's do not. I would like to connect d small x to d capital X because we know the relationship between them will involve the deformation gradient from the definition of the deformation gradient. To do that, I can write the coordinate differentials in terms of d capital X by taking the gradient of the convective coordinates with respect to position capital X. That's what this grad means here, okay? Take the gradient with respect to capital X. When I do that, I get the dual basis elements in the reference configuration. The same discussion we had before, it's just I have to be mindful of the gradient that I'm taking here. Alternatively, I could take the gradients in the current configuration, the gradients of the same coordinates expressed as functions of the small axis. And the small grad here is a gradient with respect to current position, so I use a different notation here to distinguish the two different types of gradients. And this would give me G super I dot d small x. This is again the dual basis. Okay. If you don't like what I've just done, you can just notice that, for example, d theta j can be written in this way in terms of the Kronecker delta, sum on I. Use the bases in the reference configuration to interpret the Kronecker delta. This one is d capital X. So we have a capital G super J left over. So that gives you the same result. Let's invoke the definition of the deformation gradient, f d cap x equals d small x. Again, if you go back to the beginning of the course, that's just an application of the chain rule. Let's write d small x using this line here. And for the coordinate differentials, I'll use this formula here so that I can involve the d capital X. And now I recognize a tensor product here. This is the tensor product of small g sub I with capital G super I, all operating on dx. So this outer equation holds for all dx. Therefore, the deformation gradient has this rather simple, nice elegant formula, valid in a convected coordinate system. Excuse me. From this, we can now compute an expression for the Cauchy-Green, right Cauchy-Green deformation tensor, F transpose F. So I write F transpose on this product. That brings in F transpose operating on the small g's. That gives 3 vectors, and then tensor product of the capital G super i's, and then sum on I. So here is F. The transpose is obtained simply by interchanging the factors in the tensor product. And because I've used the I already as a summation index, in the expression for the transpose, I'll use J instead, a different summation index. Then this operating on small gi gives me G sub J dot G sub I. My writing is a bit sloppy, sorry. With a G super J left over. This would be a G super J here, if it's not clear. That goes with this. So then I have the metric G sub Ji, G super J, tensor product G super I, which is the same as this if I simply relabel I to be J and J to be I. This is the same as this. So this gives you a nice interpretation of the metric induced by the curvilinear, the convected coordinates in the current configuration. They're just the covariant components of the Cauchy-Green deformation tensor with respect to the referential dual basis. So if we could write that, we could identify the covariant components here as just these, the metric in the current configuration, subscript. You might be tempted to make the following mistake. You might be tempted to say, well, if G sub ij is C sub ij is small g sub ij, then the contravariant components, C super ij, must be small g super ij. But that would be false. The reason is, in an expression like this, to get the contravariant components, you have to raise the indices using the referential metric, because it's the referential metric that is used to derive the dual basis, or the natural basis from the dual basis, and so on, and vice versa. Doing that, then we need the referential metric to raise the indices to get the contravariant components of C on the referential natural basis. So this is the kind of thing that you know can cause problems if you're not careful. Let's discuss for a moment the notion of volume. If you remember when we were talking about the example in spherical coordinates before, I indicated that the volume measure, dV, is given by the product of the three coordinate differentials times the square root of the determinants of the metric. Maybe it would have been better if I had isolated that result separate from that example, but it's embedded in that discussion of the example. So the same is true in the referential, in the reference configuration. The coordinates are not changing, right? These are convected coordinates, the same in all configurations, but the metric is different. So we have the square root of the referential metric, determinants of the referential metric, called capital G. We know from continuum mechanics, the ratio of these volume measures is just capital J, which is the determinant of F. So by comparing these two, we simply see that J must be, if you divide d small b by d capital B, you just get this ratio, the square root of ratio of small g over cap G. And that's easy to remember. The referential density, remember, rho sub kappa is rho times J. With this result now, we have this nice formula. Rho kappa square root of capital G is rho times the square root of small g. Conservation of mass tells us that the left-hand side is independent of time if you regard rho kappa as a function of the convected coordinates and time. The same is true of capital G, of course. So the left-hand side here is independent of time, and the right-hand side is dependent on time. So taking a time derivative, you can extract your usual statement of the mass conservation equation. We were talking here about volume. That's a very simple relationship that gives you the local volume ratio. For surface area, we can do the same. So I should have a label here, kappa sub T, for the current configuration over here. Here I have kappa R. So put in the kappa sub T if you can. And what we need to do is discuss the oriented surface measure, which is the normal to the surface patch, times dA, which is essentially the area contained in this parallelogram, where the legs of the parallelogram are induced by a dx here and another dx here. So if you remember, we had this discussion in the connection with Stokes' theorem a couple of lectures ago, 1 or 2 lectures ago. And we saw that the oriented surface area measure is just this. The permutation tensor associated with this space, we call it epsilon, which has this expression, square root of small g times the usual permutation symbol, in the appropriate basis. And then we have the psi I and d eta j. If you remember, this was associated with using a surface parameterization, say a U1 coordinate curve intersecting a U2 coordinate curve. So d psi I was d theta I, the 3 coordinates, d theta I, du1 times du1. And d eta j was d theta j du2 du2. These two things are different, so to avoid confusion, we call them d psi I and d eta j. So we have that. But these are just, again, induced by the convected coordinates. The coordinates are not changing, so we have the same coordinate differentials here in the reference configuration. But of course, the oriented area measure is different. It's orientation capital N, area D capital A. We need the appropriate permutation tensor here, which is square root capital G times the same permutation symbols, and we have the appropriate basis here. So from this expression here, we can read off the covariant components of this equation. Would just be n sub k dA. So n would be n sub k small g super k, right? Read off the covariant components here, you just get what's shown here. Do the same thing here. Use n as n sub k capital G super k. So you read off the covariant components of this equation, and you get this. These two things are common to both equations. Immediately then you see that n sub k dA divided by the square root of small g is the same as capital N sub k d capital A divided by square root of capital G. So multiplying through by root small g, we get this expression. And this is our J, determinant of F. So we have this expression here. But what's important to note is that this equation is only valid for covariant components of the two vectors with respect to the two different bases. To recover the vector expressions, we'd have to multiply through by the appropriate basis elements here. So to recover n, from this, we multiply by small g super k. And then we invoke this equation. I want to involve the referential basis so that I can extract the vector capital N. I can do that by using, so here's the referential vector. If I do this, if I multiply by this tensor, this becomes the Kronecker delta, which when summed on I gives me the gk that I need, with the n sub k left over. This object in parenthesis is the transpose of the inverse of F. To see that, I guess here I've committed a kind of a crime. This left-hand side is supposed to be exactly the same as this with capital G subscript I. So you can see things can get, you can make silly mistakes if you're not careful. This left-hand side, as I've written it, has no meaning because the repeated indices must be one up and one down, and that's not the case here. So this left-hand side is intended to be exactly that parenthesis. If that's true, if this claim is true, then the transpose of this should be F inverse. So the transpose of this should be F inverse. So let's check that. Here we have F. Assuming the statement be true, this must be F inverse. We get F capital GI tensor product small g super I, but F capital GI from our earlier expression for F is just small g sub I, and then I have the tensor product with small g super I. That's just one of many ways of writing the identity. So indeed, this is F inverse, and therefore this must be the transpose of F inverse. And immediately then, we've extracted the Piola-Nansen formula. Small nda is cofactor, I've got the J in front, F inverse transpose, it's cofactor F, cap N, d cap A. So you see you can get quick and easy derivations of these transformation formulas by using convective coordinates. You just have to have a good facility with the use of the notation. Speaking of notation, I have a lot of it going around. In the current configuration, I've used small g for the metric, and so on and so on. I use gamma, as we had previously, for the connection coefficients. Here, these are the so-called Lavichavita connection coefficients, also known as the Christoffel symbols, associated with our Euclidean space in our deformed configuration. The permutation symbol we've already seen, permutation tensor. The contravariant components of that are this, if you go back to your earlier notes. And we'll need covariant derivatives. So when I have a covariant derivative based on these connection coefficients pertaining to the current configuration, I'll use a semicolon as I've done before. For the reference configuration, I need to change the notation in order to preserve the distinction in these variables. I used the capital G's already. I'll use a gamma with a bar on top because the gamma is a very well-entrenched notation. People don't want to deviate from it. So I'll distinguish these gammas, these connection coefficients, from these by using an overbar. I'll put an overbar on the permutations tensor. get the referential permutation tensor, contravariant components here. And if I need a covariant derivative based on this connection, I'll use a vertical stroke instead of the semicolon. All these notations are entirely standard. People often will either use semicolons or vertical strokes or maybe the grad symbol to denote covariant derivatives. And so I'm not inventing new notation, I'm just fixing a convention for us to use. From this we can, from this formalism, we can extract an expression for the covariant components, for example, of the Lagrange strain. Right C we've seen in terms of its covariant components, and the identity we can write in terms of, one way of writing it is in terms of the referential metric on the referential dual basis. Put the half in front. This parenthesis combined with the half then must be my covariant components of G. This expression is only valid for covariant components. For example, E super ij is not equal to small g super ij minus capital G super ij, for the same reasons that we indicated previously. So, but nevertheless, it's a simple and elegant formula in terms of, for the covariant components. The strain is just the difference of the metrics induced by the coordinate system, the convective coordinate system, with the half, of course. Okay. Any questions up to this point? Okay. I'll do something now in which the use of convective coordinates is really quite convenient. So we have our, for example, our Cauchy stress. I'll write it in terms of, for example, contravariant components on the current natural basis. Okay, second order tensor. The divergence, we've seen how to take the divergence of such an object previously. That just involves the covariant derivatives with respect to the appropriate connection, which is the gamma without the super overbar. In other words, the covariant derivative will be the semicolon derivative here, and then multiplying the appropriate basis elements. Okay, so here's our Cauchy equation of motion. The right-hand side is the inertia, and this A is the acceleration. Put this on the basis small gi and read off the coefficients. This is just the component version of the Cauchy equations of motion with respect to the current natural basis. This is the contravariant components of the Cauchy equation. Here, B super I is the components of B in the natural basis are just the components of just the projections into the dual basis, if you remember what we've done before. The contravariant components of the acceleration, that's just the acceleration, which is material derivative of velocity projected into the dual basis. So let's put this dual basis here. We're going to dot with the material velocity expressed in this way in terms of my natural basis, for example. I could express it in terms of the dual basis by using covariant components if I prefer. This is just one way to do it. Well, when I take the dot, so I have to distribute the derivative, of course, as usual, use the product rule. I have v dot j, gj, and then vj, gj dot. Gj is x comma j, and then that's all of that is dot. But in the convected formalism, I'm taking the convected coordinates, theta j, and time as independent variables. So I can interchange the order of differentiation, assuming that all those partial derivatives are continuous. That's fine. I can write x comma j all dot as x dot comma j. Right? So here I have this ambiguous notation, which I can get away with for the reasons I've just indicated. X dot, of course, is v. And if you look back in your notes, v comma j inner product g super I is just this covariant derivative. This is a gradient of v. this covariant derivative, v super I semicolon j, with a vj left over. And of course, this gives me a Kronecker delta, which gives me a v dot I. So you recognize this as the convective term in the acceleration, right, from continuum mechanics. So you get an immediate automatic derivation of the convective, of the material derivative of velocity in the convected formalism. Okay, you don't have to do this, but it gives you an elegant way of extracting that formula. Okay, the symmetry of the Cauchy stress is easy. So take the Cauchy stress, Tij, G sub I, G sub j, and interchange the vectors in the tensor product to get the transpose, right? That's the same then as this by simply relabeling the indices. Require the Cauchy stress to be symmetric, which means it's equal to its own transpose. You get this. Because this basis is linearly an independent set, that means you have to have this for each I and j, obviously. Okay, Piola stress. We know from continuum mechanics that that's just T times the cofactor of F. So that's J F inverse transpose with a T here, J given by this. I'll write T in the manner I've just done using the current basis, contravariant components on the current basis. The F inverse transpose, we went through some labor to get that. Be careful not to overuse any summation index, right? So use different summation indices. This combination brings in a Kronecker delta super J sub K. Sum on K gives me a J here with a GI tensor product G, capital G sub J left over. So inside this parenthesis, I have three vectors for each fixed J. Of course, there's a sum on I. I'll call those three vectors P super J. P super J is J, Tij, Gi. We'll call these the stress vectors associated with the Piola stress. So if Pj is this, then Pi, for example, would be this with the I and J interchanged in this definition. And of course, we have the symmetry of the Cauchy stress, which is equivalent to saying that T super Ij Gi cross Gj is 0 because this is skew in I and J, and that inner product will then disappear if and only if Tij is symmetric in I and J. So this statement then is equivalent to this one involving the Piola stress vectors. So this is a disguised version of the symmetry of the Cauchy stress. This is the sum of three vectors, G1 cross P1 plus G2 cross P2 plus G3 cross P3, all equal to 0. They're not 0 individually, only the sum is 0. We know the Piola traction, small p, is p on the referential normal. Let's use our formula, our expression for tensor p in terms of the Piola stress vectors. This brings in a dot product G sub I dot n, which are the covariant components of n in the referential basis. So we have this expression for the Piola traction in terms of the Piola stress vectors. And by the way, this gives us a way to interpret the Piola stress vectors. I can write them using the Kronecker delta this way, sum on J, P super I is this. I can interpret the Kronecker delta in terms of the referential bases, like so. This is P super J tensor product G sub J, which is P, operating on G super I, which is the referential gradient of the ith convected coordinate. Now we know that, say for example, if we put I equal 1, gradient theta 1 is the normal, not the unit normal, but it's normal to the surface on which theta 1 equals constant. The unit normal would be this. So P super 1 would be proportional to the traction transmitted across the coordinate surface theta 1 equals constant. The proportionality factor is this, the norm of the gradient here. Okay. So this gives you a way of physically understanding what these stress vectors are. They're proportional to the tractions transmitted across the surfaces on which the various coordinates are constant. Let's look at the referential divergence of the Piola stress, which we know figures prominently in the referential equations of motion. From what we've done before in the context without any continuum mechanics, just in the purely geometric context, Euclidean space, we saw that to get the divergence of a tensor, you take the comma j of the tensor and then operate on vector g super j. So there should be an underline on that vector. And then sum on j. So look back in your notes to remind yourselves of that. And we're using a referential basis to go with the referential operation here. Write the Piola stress tensor in terms of the stress vectors in this manner, and then operate each result on g super j, so there's a sum on j, of course. Now distribute the derivative in the usual manner using the product rule, like so, right? So this gi forms with this to give a Kronecker delta super ji. Sum on j, you get pi comma I, just conventional partial derivatives. This one gives you the referential connection coefficients, right? Gamma gj dot capital G sub I comma j is this, it's just this, the referential connection JJI, which sits here. If you remember, a nice result we had for all so-called Lavichavita connections, which includes the Euclidean ones in special case, the nice result we had was that this sum here with the free index I can be interpreted as the partial with respect to theta I of root g divided by square root of g, if you go back in your notes. So this complication can be written this way, in terms of only involving partial derivatives with respect to the coordinates. Okay. Well, we can define in the same way Cauchy traction vectors, like so, sum on j. When we do this, the Cauchy stress itself is just the sum of these three tensor products, right? Because this is then TJI, GJ, tensor product GI, which is the Cauchy stress. The divergence, the spatial divergence, in current configuration, is the same thing, except we have to operate with the appropriate basis. Do the same story, go through the same story, and you'll get this formula with the determinants of the metric and the current configuration. Again, partial derivatives. So that the Cauchy's equations of motion can be written in terms of these Cauchy stress vectors in this way. So let's suppose we all believe the Cauchy equation of motion. We've just recast it in this form. We'll see how trivial it is now to derive the Piola equations of motion. First, let's multiply this equation through by j. When we do that, we get rho j is the referential density. Okay? Multiply through by j, which is this. J divided by root small g is 1 over root cap g. And then root small g is j times root cap g in here. The jti, if you look back a page, are just the Piola stress vectors. So we have this, which then immediately gives you, from our formula for the divergence of referential divergence of P, gives you immediately this. So you get from the Cauchy equations of motion, you get the Piola equations with no effort whatsoever, or with a line of, in 2 lines. Okay. The usual derivation of the Piola equations from the Cauchy equations makes use of the famous Piola identity, the divergence of the cofactor of f equals 0. In Cartesians, such as you typically use in a course like 185, 287, that just reads this, where you have Cartesian coordinates small xi, referential Cartesians capital XA. This would just be the component form of this. And then the referential divergence of Piola, put in Piola in terms of Cauchy, take the referential derivative, distribute the derivative, you get this. This then would be 0 by the Piola identity. F star is, oh, by the way, so I can convert from a comma A to a comma K by using the deformation gradient, right? Because in Cartesians, F sub Ka would be partial xk with respect to capital Xa, sum on K. I just get this by the chain rule, this first term here, with the cofactor left over. This now, Fka F star Ja is J times the identity. Right. And sum on A here, I just get Kronecker delta Kj. Sum on K, I get Tij comma J, which is the divergence in the current configuration with a prefactor of J. In other words, referential divergence Piola equals J times current divergence of Cauchy. So that's the, in order to press this program through in the standard format, you need the Piola identity. And I know some of you have not seen it before and encountered some difficulty in homework as a result. We teach this in 185 to 87, but it may not be widely known. Using convected coordinates, this result comes out trivially. So let's try that. Let's use convected coordinates. We've already had a formula for a cofactor of F in convected coordinates. Small g super I, capital G sub I with a J in front. This looks just like my Piola stress, where if I put the parenthesis before the J and after the small g, that would be my Piola stress vectors. And I know how to take the referential divergence of that, Piola stress. I've just done it. We had a capital P I here. In place of that, now we put J G super I. Now, 1 over square root of capital G is the same as J divided by square root of small g. And J times the square root of capital G is the square root of small g. And now I just take this partial derivative. So I have the J, root G comma I divided by root G, the Gi left over. And then remember, Gi comma I was connection coefficient IIK, which is this, G super K. And this exactly cancels this, right? Because the summation index here is K, here it's I, but it doesn't matter, the same summation index. This is a covariant index on this partial derivative, and this should be a superscript Gi. These exactly cancel out. So in convected coordinates, you can see exactly why this is an identity. It's identically 0. And in our passage, by the way, from Cauchy equations of motion to Piola, we did not explicitly use the Piola identity in the derivation. We didn't make any use of it, right? If you recall here. So in a way, this is a more intrinsic way of viewing the subject without the need for extraneous equations like the Piola identity, which after all are identities, so they're always satisfied. Okay, second Piola-Kirchhoff stress, defined in terms of P in this way as usual. F inverse is this, we've seen before. Piola I can write in terms of Piola stress vectors like this. These two get together, make a dot product with the basis elements left over. So I induce purely a referential tensor, and these dot products I'll call S super Ki. So these are the contravariant components of the second Piola-Kirchhoff stress on the referential natural basis. They're defined, as we've just seen, this way. I can replace these Piola stress vectors by their definition that we started with. The dot product here gives me a Kronecker delta super K sub J, sum on J, and I get T super Ki with the J left over. So I get S super Ki contravariant are J times the contravariant Cauchy stress components. But this, again, is an equation only valid for contravariant components. If I want to lower the indices, I have to use the referential metric throughout. And when I use the referential metric here, I don't get the covariant components of T on the current basis, right? So here's another equation that's simple, but there's a complication concealed by the fact that it's only valid for contravariant components. However, because we have T super Ik is the same as T super Ki, I immediately get the symmetry of the second Piola-Kirchhoff stress with no effort. Okay, so this is just a recasting of routine equations that we're familiar with in terms of this, number one, curvilinear coordinate formalism, and number two, so taking the curvilinear coordinates to be convected. The reason is, I mean, it would really be nightmarish to have to deal with two sets of curvilinear coordinates, right? One for the current and one for the reference. Let's dispose of that complication simply by using a single coordinate system, a convected coordinate system. Then we are always dealing with one coordinate system that will induce different geometric objects like metric and connection in the different configurations, but it's still one coordinate system. Okay, let's have a discussion of string compatibility, which is not normally treated, at least not at a deep level, in an introductory continuum mechanics course. Ironically, string compatibility is usually well described in an undergraduate course dealing with linearized kinematics, and the reason there is that it's much simpler in that setting to deal with. In the nonlinear case, we can proceed as follows. So we know that, or we stipulate that the configurations of the body reside in the normal Euclidean space of our common experience, right? So we see these in a space that we identify as Euclidean space, going back to the time of Euclid and before, right? So we know in a Euclidean space, for example, that our so-called Riemann-Christoffel tensor, this four-index fourth-order tensor, is zero, right? We've seen that before. In fact, it's so we know to get this, we simply needed to introduce a connection defined in the way we did before in terms of the dual basis and natural basis. For example, G super K sub Mj is G vector G super K dot G sub M comma J, and that induces always zero value for the Riemann-Christoffel tensor. This is, so we would say, because we associate the Riemann tensor, Riemann-Christoffel tensor, with curvature, at least in the examples to which we apply it in differential geometry of surfaces, 2 dimensions, or in gravitation, which is 4 dimensions, we associate the Riemann tensor with curvature. We could say Euclidean space is curvature-free or a flat space, okay? So a 2D Euclidean space, for example, would be a plain sheet of paper. That would be a flat space as an example. It's not the only one, but that's an example. So we live in a 3-dimensional flat space in terms of our terrestrial perception of how the world is. So for that reason, the connection induced by our convected coordinates in the current configuration should give rise to a Riemann tensor which is identically zero. Here's the connection we're talking about. This is we called it before the Lavichavita connection. I won't confuse you by using the other names like Christoffel symbols, but this is also used. this is a symmetric connection in I and J. So here's an I and J here. This one, it doesn't seem to be the same as the symmetric part of this, right? But it is, because G sub JK is the same as G sub KJ. So I have an KIJ and a KJI. That combination is symmetric in I and J, and of course this is also symmetric in I and J. So this is the symmetric connection, Lavichavita connection. Later, when we look at a space induced by plastic deformation, we will be talking about a space with so-called torsion. I think we discussed it already, in which you can have a part that's non-symmetric in I and J, and I'm asking you to explore that in your homework, your current homework. But here's the connection associated with our Euclidean space. Incidentally, we could have in Riemannian space, curved space, we typically, a Riemannian space is a space with a connection that looks like this, a metric and a connection exactly like this, which delivers a non-zero Riemann tensor. Okay, it's just that the manner in which we obtained our particular connection induced a zero value of the Riemann tensor. Okay, I'm over-explaining it. Okay, well, remember for the covariant components of strain, we had this relationship. The strain, apart from the factor of 2, is just the difference of the metrics in the two spaces, current relative to reference. And this matrix of dual metric components is the inverse matrix of the original, of the covariant metric components. So that suggests that if we want to get a restriction on the strain, we use this expression, put it in the connection, the Lavichavita connection in the current configuration. Then we can write this entirely in terms of the referential metric and the covariant strain components. Put that result for the connection into this formula, and we get a restriction on the strains. Those are the strain compatibility conditions. Restriction involving the partial derivatives of the strains. Okay. Now the referential metric, G, that will induce our referential connection in the same way. The referential connection based on referential metric, that's the referential Lavichavita. Well, our reference configuration sits also in Euclidean space, so this connection will induce a Riemann tensor that has the value 0. So the idea is that if we construct the referential metric by using its definition, taking capital G vector sub I to be capital X comma I, form the metric, form the connection symbols from that, then automatically this should be satisfied. In other words, the referential metric will assume is such that this is automatically satisfied simply by the way we construct it. So then with the referential metric such as to satisfy this automatically, the first equation becomes a system of equations that again restricts the covariant strain components. Those are the conditions such that the strain gives rise to a configuration in Euclidean space. That's all it means. Right? The strains that of a body give rise to a deformation field. Let's put it this way. For the strains that satisfy equation 1, it looks like those were a lot of equations because each index ranges from 1 to 3 separately, so there are 81 equations. That looks horrible. We'll show it's not so horrible in a moment. Those equations, if satisfied by the strains, will ensure that there exists a deformation, small x, which places the body in Euclidean space. Right? In other words, there's a position field associated with the strain field. Okay? You can begin to see why we never talk about this in an introductory course in continuum mechanics, because it's just too much. Well, it turns out to be somewhat more convenient to deal with a fully covariant version of the Riemann tensor, the Riemann-Christoffel tensor. We can obtain that simply by lowering the index k using the metric, just in the usual way that we've described raising and lowering indices. So we'll take this to be the definition of the fully covariant Riemann tensor. So equation 1, which requires that all of these to be 0, is equivalent to these being 0 because G, being positive definite, is invertible. Okay? So the only way these can be 0 is that, well, if these are 0, then automatically these are 0. But the converse is also true. These being 0 guarantees that all of these are 0 because of the invertibility of G. So equation 1, the vanishing of these, is equivalent to the vanishing of the fully covariant Riemann tensor. And this version of the compatibility equations is a bit more straightforward. Okay, we'll call that equation 3. Equation 2 defined the connection, and equation 1 was the original constraint. So we just have a small job to do, which is to drop the indices, use the definition of the R with a superscript k, and just drop the index k using the metric throughout. So that's given here. So these two parentheses combined are just these, if you look back in your notes, the definition of the Riemann-Christoffel tensor. Okay, so let's do a bit of index gymnastics, a little bit of algebra. Let's look at the first combination, G, P, K times this mess, gamma K, MJ, comma L. Let's see if we can get anywhere by combining these two terms into a derivative and then compensating by subtracting off the derivative of the metric. Okay, just using the product rule. Well, this thing here inside the parenthesis, remember we defined before, if you look back in your notes, around page 39, I believe it is. Look back in your notes, we defined a connection symbols with all indices downstairs to simply be the index lowered version of these original connection symbols. So we'll do that here. Take the comma L as indicated, then repeat this. What I need is this combination. So let's look at the top line. This combination then is just this. Let's see if, yeah. So I have a gamma IMJ, KIL, IMJ, KIL. Let's see, so I'm doing this. I put, I'll just put this over here, and then I bring this down, right? And put it right here. Except I've dropped the index K by using the G here. So I have a PIL down here, a pill. I'd like to see if I can get rid of these partial derivatives of the metric. I can do that if you look back on page 39 of the notes. I won't do that here. We had that derivative of the metric is this combination of the index lowered connection symbols. Okay, and this formula is very general. It's true even for a non-symmetric connection with torsion. So if I use that in here, the PIL terms drop out, and I just get this left over.
PIL.
Yeah. Is there a question?
Yes, Professor. In the equation above, is there a GPK in front of gamma PIL in the last term?
PK KIL gives me a PIL over here. So GPK, gamma super K IL, is gamma sub P IL from the definition, the same definition.
Oh, I see.
And then I have the IMJ left over. Here, this one is this one. And then I already have the GPK on this, right? So I don't need it anymore. I just bring it down. That the GPK times this is equal to that, which is here and here in the last term. But I haven't done this term yet. GPK gamma super K IL is G sub P IL. And then I have a gamma IMJ left over. So if you have a pencil and paper, I think you can verify this. Okay?
Yeah, okay.
Yeah, it's what one quickly gets index blindness after a while. It's true. So you have to, you have to be good at bookkeeping, right? It's this a sign of a work for an accountant more than a scientist, right? This is purely bookkeeping. Okay, so we have this result by using this formula from page 39, if you go back and look. Now, so I've taken care of the first line here. Now I want to do the same thing for this. The only difference between this line and this one is I've interchanged L and J. The second line is the same as the first line if I interchange L and J. So if I interchange L and J in this formula, I get this. Okay. Now, I want to get the fully covariant Riemann tensor, I must subtract. I must take this and subtract this line. So I subtract these two, and that gives me this expression here. So my fully covariant Riemann tensor can be expressed this way in terms of the index lowered connection symbols, which I've defined. Gamma with a sub PMJ is G sub PK gamma super K sub MJ. Consistent definition. The first index corresponds to the lowered index on the gamma. Okay. Okay, so now I have this. I would like to show that this index lowered Riemann tensor actually has a nice major symmetry property. If I take the pair PM and interchange it with the pair LJ, I don't change anything. So I'm aiming to show that, because if that's true, then the compatibility conditions are greatly simplified. So here I have RPM-LJ. If I just, everywhere I see a PM, I put an LJ and vice versa, in the same formula, I get this. So I'll let you do the accounting to show that that's true. I would like to rewrite this in a way that's convenient, this third term. I can drop the index on the gamma and raise the index on this gamma, and I get this here, just by using the metric twice. The subscripted metric and then the superscripted metric to raise the indices, and then I'll get a Kronecker delta in between. You can verify that this is exactly the same as this. Sum on I, just as we have a sum on I here. And now I'll just interchange the factors in these products. This is ordinary multiplication. ILM, I'll use now the symmetry property of the Lavichavita connection. Gamma ILM is the same as gamma IML. And also IJP is the same as IPJ. So I can rewrite this way. This one I can write as IMJ because of the symmetry of the connection, and IPL because again the symmetry of the connection. So when I do that, So if I want to show that this is the same as this, that's the same as showing that this difference is 0. Let's form that difference now that I have these two expressions. I get PMJ comma L, subtract this, I subtract LPJ comma M, then I have a minus PML comma J, subtract LJM comma P, which I've done here. All the other gammas disappear because I have IML, IPJ, that's the same as this, minus IMJ, IPL, subtract the negative, I add that, and these terms disappear. So I have some simplification. I have not yet proved that this is 0 as I wish. But let's go back to our Lavichavita connection. If you look at page 40 in the notes, so sorry, here it's, I rely on you to go back to that page on your own, since you have the notes. I need these combination of derivatives. I can start from the fact that 2 times the index lowered gammas are equal to these. That's just the index lowered version of the Lavichavita connection. If you look back at equation 2, I think we called it in today's lecture. Again, it's symmetric in MJ because this is obviously symmetric in MJ. This is the same as G, PJ comma M. And this is an PM comma J, PJ comma M. This combination is symmetric in M and J. This is symmetric in M and J. So these steps pertain to a symmetric connection, Lavichavita. Okay, so let's see what we can do. Let's add these two terms. And I'll bring the 2 in because of this here. When I do that, I get a bunch of derivatives of the metric if I add those 2 terms together. Okay. Then I want to add these 2 terms using the same formula. And I get this. Now, I subtract this from this, which means I have this right-hand side minus this entire right-hand side. So if I do that, and I put the 2 on the other side, I get these terms, and I'm collecting all the terms that have the same indices associated with the derivatives. Because for a C2 metric, I can interchange the order of differentiation. When I collect all the terms that have the same derivative indices, I see that they're the same. In other words, they cancel. Each parenthesis cancels because, for example, this one is equal to that. This is equal to, because of the symmetry in the metric, this disappears. These are all disappear. So each term on the right-hand side vanishes, which means indeed the index lowered R's have the major symmetry that we claimed in the first place. So this is true in our Euclidean space, because the Euclidean space is a space in which the connection is the Lavichavita connection, which is the only thing we've used so far. Interestingly, this is also valid in a Riemannian space, which a Riemannian space being a space with a Lavichavita connection. Because nowhere in this discussion did we use the fact that the Lavichavita connection is induced by a position field. If we just write down the Lavichavita connection in equation 2, then this will always be satisfied. So it's true also in any Riemannian space. A special Riemannian space is the Euclidean space, special case where the Riemannian curvature is 0. Okay, what does that do for us? Well, remember from the definition of the Riemann tensor, it's skew in the second pair of subscripts. Just from its basic definition, if you look back the first time we discussed the Riemann tensor, it's skew in L and J. So the symmetric part in L and J, which is indicated by the round parenthesis, as we've done before. The part of the Riemann tensor that's symmetrized in L and J is identically 0 just from the definition of the Riemann tensor. Of course, this would be automatically true in a Euclidean space, which has 0, the entire Riemann tensor is 0 anyway. But the point is, this is always 0 in any Riemannian space, or actually in any space, because from the definition of the Riemann tensor in terms of the connection coefficients, it was automatically skew in this L and J. So let's see, the same then is true for the index lowered version, the fully covariant Riemann tensor. Because to get that, we just drop the index k with the g sub pk. And if we symmetrize in L and J, right, then this will be 0. So the fully covariant Riemann tensor is automatically skew in the second, in the third and fourth subscripts. This, however, says it's also skew in the first and second subscripts, because RPM LJ symmetrize in L and J, you get 0 from this. Symmetrize here in L and J, you get 0. So it's also skew in the first set of subscripts because of the major symmetry we've just proved. So the Riemann tensor is the same as if you skew symmetrize the first and second, and skew symmetrize the third and fourth subscripts. You lose no information by replacing the Riemann tensor by this, where you only look at the skew symmetrized part in P and M and the skew symmetrized part in L and J. Because all these symmetries, the minor symmetry in the first pair of subscripts, that's 0, and the minor symmetry in the second pair of subscripts is 0. So that reduces greatly the number of non-trivial Riemann tensor components. So to obtain these results, I want to remind you that we used only the Lavichavita connection. We made no use of this Euclidean concept of a position field. So these results are also valid in any Riemannian space defined to be a space with a metric and a Lavichavita connection derived from it. Okay, so what's the upshot here? Because of this equation, 5, R is skew in P and M and skew in L and J. So we lose no information by doing this. We retain all the information in the Riemann tensor by multiplying through, for example, by permutation super IKL, permutation super JMN. This is skew in K and L, skew in M and N. The sum on K and L loses, it retains the skew part of K and the skew symmetrized part in K and L. You lose no information on that sum. Likewise, by summing in M and N, you don't lose any information there either. So in fact, the Riemann tensor we have so far in our Riemannian space and hence also in Euclidean space is actually equivalent to a second order tensor defined in this way. I'll call it pi super ij, since I'm running out of notation, well, running out of alphabet. So I'm claiming that these two tensors are equivalent. So saying that the Riemann tensor is 0, which is our compatibility equations, is equivalent to saying that this tensor is 0. That's a lot less to worry about, because this is simply then 9 equations, right? The second order tensor is associated with 9 equations, nine quantities. I have not yet proved that this R is equivalent to pi. To do that, I have to prove that this equation is invertible. Obviously, given R, we compute pi, but we'd like to know, if we start with pi, can we compute R? If so, then this establishes the equivalence. So to do that, let's start with a pi like this, defined this way, and multiply through by some permutation tensor components, I and j, sum on I and j, and I'll use PQ and RS to avoid any conflict with the summations on the right-hand side. And the 1/4 we'll see will disappear when I do this. So I have 1/4 IPQ, IKL, JRS, JMN, and so on. I can now use my E delta identity, which you can recall from our discussion of Stokes' theorem. I get a Kronecker delta KP LQ minus LP KQ. The sum on K and L here involves the Riemann tensor. So I get in place of KL, I get PQ in this term. Then I subtract, in place of LK, or in place of KL, I get QP, right? K is replaced by Q, and L is replaced by P. So I get this difference. But I know that I have the skew symmetry in the first set of subscripts. In other words, minus R sub QP is the same as plus R sub PQ. So these add together to give me a 2, which goes with a 1/4 here to give me a 1/2, and I just get this. Now I can do the same for the second product of permutation tensors, right? Use the E delta identity again, and P and Q are passive. I have a sum on M and N here. So I replace, in the first one I get an RS. In the second one I get S replacing M, I get SR. Again, I have that minus R sub SR is the same as plus R sub RS. So these combine to give me 2 of these, which goes with the 1/2, and therefore the 1/4 disappears. So this should remind you of what we do when we talk about axial vectors or axial vectors of skew tensors in continuum mechanics or in dynamics, right? Angular velocity is the axial vector of the spin and so on. We do exactly the same procedure, except we use the permutation 1 time instead of 2 times, and we have a 1/2 in front instead of the 1/4. Exactly the same operation extended to 4th order tensors. So that establishes then that R and pi are equivalent. So the statement R equals 0, which is our compatibility equation, is entirely equivalent to this pi equals 0. So instead of having, this horrible set of 81 equations we have to worry about, we have 9 equations of compatibility. But it's actually better than that. And we're at the end, we're coming to the end. We can show that this pi is actually symmetric. Let's write down pi ji just by going back to the definition of pi and interchanging I and j to get pi ji. So I do that down here. I just interchange the I and the j, nothing else. So I have this. Now I can invoke the major symmetry of the R tensor to replace KLMN by MNKL. Right? Now, these are simply summation indices. K and L are summed, M and N are summed. It doesn't matter what I call them. Let's replace KL by MN consistently. So wherever I see a KL, I replace it by MN. I haven't changed anything. Wherever I see MN, I replace it by KL. I've changed nothing. So this now, pi ji is the same as this. But if you look back at the definition of pi, I had an E sub IKL in front, or E super IKL in front, E super JMN in the back, but these are just conventional products, they commute. I have pi ij. So pi ij is actually symmetric, which means the skew symmetrized part of it is identically 0. You don't get any information at all from those compatibility conditions. You simply get 0 equals 0. So the only remaining content in the compatibility equations is this. Pi ij equals 0 is equivalent then to the symmetric tensor. Pi ij is a symmetric tensor that's equal to 0. That's six equations, right? Because there are 6 entries in a symmetric tensor. And that explains what you've heard about in your undergrad days, that there are 6 independent equations of compatibility in 3-dimensional space. In 2 dimensions, in plane strain, for example, you have only 1 equation of compatibility, as it turns out. In 3 dimensions, you have 6. And that gives you 6 restrictions. That's good, because otherwise we'd be in trouble, right? That gives you, I don't know if I can get rid of this symbol at the bottom here. That gives you six equations that restrict the 6 variables E sub KL, because E is symmetric as well. And that gives you a set of now nonlinear, in the general context, nonlinear differential equations. There's second order in the strain derivatives of strain that must be satisfied. And in your next homework, I'll ask you to fill in the details to get the explicit strain compatibility conditions in the nonlinear case. So to do that, you would just come back to this lecture and fill in those steps in this last slide here. Okay, I think we're ready to stop for today, or unless there are any questions. We'll see when we talk about a geometry associated with plastic deformation, we'll revisit these compatibility conditions and show how they're, an elastic strain will be combined in a compatibility equation together with so-called dislocation density, which turns out to be the torsion of the connection associated with the plastic deformation, so that in the presence of plastic deformation, there must be an elastic strain distribution, which means the body is stressed. You cannot have a stress-free global configuration. So dislocations induce stress simply by virtue of compatibility. We'll talk about that in the near future. Okay, any further questions or any questions at all? If not, I will see you next time and see you in office hours tomorrow night. Okay.